We've got our formula up top. This is our formula for integration by parts. The integral of u dv is equal to u times v minus the integral of v du. The first example we're going to do is actually, I would say, the canonical integration by parts example. Almost every textbook is going to start off with this example because it really highlights the method of integration by parts. Okay, so if we want to integrate x times e to the x dx, the first thing, well, let me kind of tell you, this is what we're thinking of. So this is my thought bubble, or this is how you should be approaching it, right? And I've got glasses, so let me put glasses on. But you should be thinking how can I rewrite this integral? If this is the integral of x times e to the x dx, I need to write it as the integral of u dv. Okay, so I need to know what is u and what is dv. Now, I've got kind of some options looking at this. I could pick x is my u, and then that leaves e to the x dx as my dv, e to the x dx. Now, if u is equal to x, then what is du? Du has to be dx. And if dv is e to the x dx, what is v? V must be e to the x. So my first step is to try to find u and dv. Right, so step one, let me use a different color. Step one is to try to choose u and dv. Step two, once I've got u and dv, I need to figure out du and v, right? So if I've got dv, I've got to ask myself, what was v in order to give me that for dv? Now, it's usually easier to compute du because you have u, so you just take your differential. Step three is going to be to use the formula and hope that you have traded in your original integral for an integral that is easier to solve, right? So here's the idea, is that this one is the original integral, and you're going to trade it in for this integral. So you will still have to compute an integral, but the integral that you have to compute should be easier to compute than your original integral. So let's go ahead and see how this plays out with our first example here. So we know that we've got the integral of x e to the x dx, and if u is equal to x and dv is e to the x dx, so according to my formula, right, so I've got the integral of u dv is equal to uv minus the integral of v du. And now my u, we said my u is x, and my v is e to the x, okay, so I'm going to write that there, minus the integral, now what is v? E to the x, what is du? Du is dx. So I started out with the integral of x e to the x dx, right? And I said, I don't know that. I don't know how to do that one. But now look what I need to do. If I can figure out the integral of e to the x, which I can, I know that's just e to the x plus a constant. Now, let's see. Don't you get out of here. Go on. If I can figure this out, then I've got my answer. So it turns out that the integral of x e to the x dx is actually equal to x e to the x minus e to the x plus c. And we could factor out an e to the x, and we would have x minus 1 plus c. Same answer, right? So that is our very first example of using integration by parts. Let's do this second example here. So remember, our step one is going to be to try to guess, or try to make a good choice for u and dv. Now looking at this, I think I'm going to have u equal to x squared. Okay, so I have u equal to x squared, and my dv is going to be the remaining ln x dx. Lots of times students will forget this dx here, and you will run into trouble because your parts won't match up at the end. Okay, so you want to be very careful and make sure that you don't forget your dx at the end of your dv. Okay, so now once I know I've made my decision about u and dv, I've got to figure out what is du, and I've got to figure out what is v. Now du, like I said, should be easy. Du is going to be 2x dx. How did I get that? I used my choice of u equals x squared. Again, don't forget your dx. The dx is important. For v, I've got to figure out now whose derivative is natural log of x. Whose derivative is natural log of x? I might be tempted to say 1 over x, but that's actually not true, right? Because if I take the derivative of 1 over x, I'm going to get, right, because isn't that x to the minus 1? If I take the derivative, I would get minus x to the minus 2 dx. And that's not what I have. So I say, nope, that's not it. Now, what is the integral of natural log of x? This actually is not such an easy thing to figure out, right? So what do I say? I say, it must be that this is not a good choice for u and dv because I don't know v. So I've got to try again. So let me try again. Let me see. Maybe this time, let me kind of start with the new. I've got this integral of x squared ln x dx. So perhaps I should try u equal to ln x and dv x squared dx. Okay, so see how I'm kind of coupling this x squared dx. All of this is my dv, and this is my u. Now let's see if I can make a little progress here. So I've got u and I've got dv. What is du? Du is going to be 1 over x dx. If dv is x squared, what is v? X cubed over 3. So according to my formula, the integral of x squared ln x dx is going to be equal to, so it should be uv minus the integral of v du. So what's u? Ln x times v, x cubed over 3. So I'm going to put x cubed over 3. Minus the integral of v, which is x cubed over 3, times du, times 1 over x dx. So now I ask myself, because I still have an integral, right? I still have an integral. I need to integrate x cubed over 3 times 1 over x. I can simplify this, though, because this 3 in the denominator, I'm pulling that out and making it 1/3. And then I've got x cubed divided by x. That's just going to be x squared. And now I know the integral of x squared dx. That's going to be x cubed over 3. I've still got this 1/3, right? So x cubed ln x over 3. So in this case, plus c. In this case, my trade-off paid off. That rhymes. My trade-off paid off because what I was given...
It's 15:30.
What I was given was an integral that I didn't know how to work with. And I traded it off for an integral that I do know how to work with, right? I do know how to evaluate this. So we can simplify and get our final answer. Let me add a page below. So we'll get as our final answer, let's see here. Copy. So for our final answer here, we'll get x cubed natural log of x over 3 minus x cubed over 9 plus a constant. Okay. I just want to show one more example, kind of as a beginner. This is the hard, right? So if we go back and look at these 3 examples that I've chosen, the first one, like I said, this one is the easy. This is the basic. It's what everyone starts off with when they're learning integration by parts. The second problem is medium. It's medium because your first choice of U and dV is incorrect, right? And so you have to understand that you have to try something else, right? So that's what makes it medium. And this last one here is difficult. What's going to make this one difficult? Two things makes this difficult. Number one, this is a definite integral, so we're going to have to work with endpoints. And number two, if I could just zoom in, what is that? What is that? Who even knows what that means, right? So in order to do the problem, you have to remember or learn or Google it. What is this? This function is actually called cinch. Cinch. So let's write that down. Once you know what cinch is, what function cinch is, things actually aren't that bad, okay? So on the side here, I'm going to write down the formula for cinch. Cinch is the function that comes up a lot in engineering. So cinch of theta is equal to e to the theta minus e to the negative theta over 2. Okay, so this is very prevalent. It's called hyperbolic sign. So the H is for hyperbolic, used in building certain types of bridges. Okay, so now the first thing I'm going to do is rewrite my problem. I like to solve these by first finding my indefinite integral and then plugging in my endpoints. So y cinch dy is going to be equal to the integral of y times e to the y minus e to the negative y over 2 dy. Okay, and then I can rewrite this by bringing out the 1/2. So I've got a factor of 1/2 in that denominator. I'm going to bring that out. So I've got y e to the y minus e to the negative y dy. Now the next thing I'm going to do is distribute this y. So I'll have the integral of y e to the y